don't have much, I don't think I have much experience, don't have much direct experience in industry, but my daily work involved practicing data science in the field with messy data, complex dependency, high-dimensional headaches, and also forecasting. So from that, in that sense, I'm a practitioner of data science, technology. So in today's presentation, I want to share some of my experience in working with data analysis from statistical point of view. For example, we have some data coming from complex dependence structure, and we want to build up some data-driven statistical model for to predict some kind of unknown stochastic mechanism, and then we develop some optimization procedure in order to learn the model, and then trying to figure out statistical property of the machine learning method. So altogether, you will see the idea of statistics, machine learning, optimization, they can come together to illustrate, to illuminate interesting phenomenon for complex stochastic phenomenon. So in today's presentation, I want to talk about this work based on my collaboration with former students and collaborator. The title is Uncovering Causal Interaction and the Network Dependency in Temporal Event Streams. Yeah, by the way, I also want to thank the organizing committee for great work in organizing this wonderful workshop. This is my first time attending the prestigious ISF, so I'm extremely excited to be here. All right, so this is the brief outline of my presentation. In the first part, I'm going to talk about, yeah, I guess I better stand in this place. Yeah, in the first part, I'm going to introduce some background and motivations for studying the multivariate temporal point process for modeling the event stream data. And at the core of the multivariate temporal point process is the some kind of random process called conditional intensity function, which is unknown in practice. And then we want to develop some kind of statistical data-driven models to model this conditional intensity function that can be useful to capture causal network, causal pathways, and the network structure. And in particular, we want to develop some causal directed acyclic graph constrained structure learning methods. In order to learn this model with the causal structure, we want to develop some optimization algorithm in order to learn the directed acyclic graph constraint estimator. So the second part is some kind of modeling method, and the third part is some kind of learning method using optimization algorithm. And the next part is we want to learn statistical properties, statistical insights of this new structure learning methods in a high-dimensional setting. In a high-dimensional setting, many times we want to incorporate the sparsity, the sparse feature. So naturally, we want to consider the sparsity regularization. So that's why in part 4, we want to consider two scenarios. The first part, without using sparsity regularization. And the second part is using sparsity regularization. We really want to figure out what is the difference between using the sparsity and not using sparsity regularization when the causal structure is present. And the next part, we want to present some numerical experiments using simulation studies and also real data analysis coming from two different kinds of real-world application. One is from computational neuroscience using neuron spectrum data, and the second one comes from internet protocol television record data. And the last part is some kind of concluding remark and further discussion. All right, so this talk is a little bit technical because I really want to present some details connecting statistical modeling, optimization, and statistical property. So this part, I want to introduce what is the so-called multivariate temporal point process. All right, so multivariate temporal point process is actually an extension of the Poisson process. The Poisson process is commonly used in application to model the event arrival time, like telephone call, etc. But Poisson process has some limitation. For example, it is memoryless, right? So because of its limitation, people want to extend Poisson process to more general situation that can be useful to model more complex physical process. So this is the so-called multivariate temporal point process. So multivariate temporal process refers to random occurrences of a specific type of event. This event varies depending on different context. For example, in neuroscience, people are interested in looking at the event called neuron spike theory because this is connected to cognitive activity of human brain. And in epidemiology, people are interested in studying the contagious disease incidence. One incidence corresponds to one specific event. And there are many other cases like e-commerce transactions or user posting in social network, etc. There are other interesting applications, for example, earthquake outbreaks over time, right? So those occurrences, they are not regularly distributed. Actually, the occurrence time are highly random. So that's why it is important to study the random phenomenon related to the event occurrence time. So when we talk about the multivariate case, we have altogether D nodes, and the data are represented as D sequences, T1, T2, up to TD. And at every node D, the Tj corresponds to a sequence of strictly monotone increasing sequences, time-ordered event time. So for example, if we look at one specific TJL, TJL represents the occurrence time of the else event during an experiment of duration T. T is the total time length T, depending on the experiment. And what is the research objective? So for this type of data, people are interested in extracting the dependency structure among nodes within the network from the observed D sequences of event occurrence times. So let's look at some specific example. So this example comes from computational neuroscience. So suppose we just look at one simple case. In certain neuron ensemble, we have 5 neurons. So on the left panel, we can see there are 5 rows, right? So each row representing the sequences of neuron spike varying time. For example, there are 5 rows that corresponds to 5 neurons. The neuron spike varies the occurrence at highly irregular time points. Yeah, this doesn't work. So you can see each vertical line corresponds to the time that neuron spike fails. And the occurrence time, they are highly irregular. And for different neuron, the density of the event occurrences are different. For example, for the fourth neuron on the first row, we can see they are much more dense, right, than the other neurons. And on the right-hand side, this is the network graph consisting of 5 nodes. So each node corresponds to one of the neurons on the left plot. And on the right-hand side, we can see there are some kind of interaction among the nodes. For example, node 2 with an arrow to node 5. That means node 2 will excite node 4. And the node 5 also excite node 4, node 3. So that's why we can see on the left-hand side, the occurrence time for neuron 4 is more densely distributed. So here I use the red color to indicate the excitatory effects and blue color for inhibitory effects. And also I want to mention, for this type of network structure, people are not only interested in reconstruct the network graph, but also they want to learn some kind of causal pathways. So here, we are particularly interested in learning the directed acyclic graph, abbreviated as DAG. Yeah, why this is important? I can mention this paper. Yeah, this paper was published last year in Science, titled Directed and Acyclic Synaptic Connectivity in a Human Layer 2 to 3 Cortical Microcircuit. So this paper provides strong scientific motivations for studying the so-called directed acyclic graph, because it can indicate the directionality of the causal interaction and also information flow from one node to other nodes. All right, so this is some numerical graphical illustration. Now, in our setup, we want to introduce some basic setting and notation for the sake of discussion. So I want to introduce 2 notation. The first one is the counting process. Yeah, counting process just counts the total number of events, occurrences, up to a time t. Yeah, this is small t. So this one is, we know this is a piecewise constant, the path, right? And from the counting process, we can define another important quantity called conditional intensity function. Yeah, this notion comes from Rubin's paper published in 1972. But Rubin's paper only focuses on one node instead of multiple nodes. So in this situation, the conditional intensity function can be defined as this limit of the conditional probability. So Ft, what is Ft? Yeah, Ft basically collect the entire historical data up to time t across all nodes. And the lambda j means an individual node j. Lambda j t given Ft, yeah, according to this definition equation 3, represents the instantaneous rate of event occurrence per unit time. So from probabilistic point of view, people define this conditional intensity function in order to capture the stochastic or probabilistic mechanism of the temporal process. All right, so intuitively speaking, we can see this conditional intensity function at individual node J utilize the event history of all nodes up to time t in order to predict the instantaneous event rate at time t. But in practical application, yeah, we don't know this conditional intensity function. It's purely, it's a random process, random function, but we don't know. However, it governs the underlying temporal process. So it is very necessary for us to develop some data-driven model. So in this page, in the next section, we want to develop some data-driven statistical predictive modeling that capture the causal pathway in the multivariate temporal point process. All right, so this is the model we developed. We developed some continuous time predictive model for conditional intensity function using this functional form. So on the left-hand side of this equation 4, I highlight 3 parts. These 3 parts play different role. The first one, W0G, this is the baseline intensity parameter relating to the node G. And also the other two. The other two, let's see, WIT. Yeah, WIT corresponds to some internal history dependent variable. Yeah, basically it plays the role of endogenous network variable, because in the real data application, we don't have additional covariates. What we have is the sequences of event streams of occurrence time. So the endogenous network variable can be designed in a way, try to mimic some useful predictor. So here we define this endogenous network variable using this nonlinear transformation G of some empirical rate. So the empirical rate depends on the time lag constant psi. We can use 1 unit time or multiple time lag in order to predict the conditional intensity function. I want to focus on the middle part, WIG. Yeah, WIG can be regarded as some interaction parameter between node I and node J. And altogether, WIG putting together in the weighted adjacency matrix W, yeah, the weighted adjacency matrix W play an important role in the network study, right? So this one will specify the directional causal relationship among nodes and will introduce causal directed graph with a node set V and edge set E, right? So the edge set E corresponds to the directed edges such that the graph parameter is non-zero. All right, so at this moment, we introduce this predictive model for the conditional intensity function with the graph parameter. Now, this is still not the directed acyclic graph. So in the following, we want to assume that the network structure has the directed acyclic feature. So we want to model the causal structure where directed acyclic graph, DAG. And what is DAG? Yeah, formally, a graph G is called a DAG if it contains no directed graphs, right? So the definition is short, but in reality, if we want to check whether a graph is a DAG, we need to, in general, people need to enumerate all subsets to check whether it contains a directed cycle. So I want to use this figure 2 to illustrate different type of directed graph. This panel A is a directed acyclic graph containing no cycles. Yeah, we can check all possible pathways. And in the middle, panel B also give us a DAG without cycles. But as a comparison, if we look at panel C is actually not a directed acyclic graph because it contains several cycles. Yeah, for example, 2 to 5, 5 to 4, and 4 back to 2. So this is one loop. So this is not a DAG. In our study, motivated by the scientific study, we want to model causal structure using directed acyclic graph. Let's see how to incorporate the directed acyclic graph into the causal structure to learn the network structure. All right. So we start with some optimization problem using a loss function. So in this situation, the loss function corresponds to the negative log likelihood function for point process data. Yeah, this is for equation 6 is for individual node, and in equation 7, the LW, the loss function, is the joint negative log likelihood function. And the second part is some kind of penalty term. So we can use weighted L1 penalty subject to the constraint. The constraint is the underlying graph is a DAG, right? So it looks like this is some constraint optimization problem. And how to solve this optimization problem? I would say this is NP hard. In the machine learning literature, this is well known to be a challenging problem to learn a directed acyclic graph. So 2 questions. The first question, how can we solve this optimization problem under the combinatorial DAG constraint? Second one, if we are able to solve the optimization problem with solution, what will be the statistical property of the solution? So in the following, I'm going to focusing on these 2 parts. One is optimization problem. The other is statistical property or statistical issues. Right, so let's see how to solve this DAG constraint estimator. All right, so first one is we want to find out some simple way or manageable way in order to characterize directed acyclic graph. Yeah, before this paper, this 2018 NIPS paper, we don't know what is the characterization property for the DAG. So this paper, the important contribution of this paper is provide a necessary sufficient condition for characterizing a DAG. So the condition is HW is equal to 0. W is the weighted adjacency matrix. And what is W? W is called Dagny's function. It is defined in equation 11. So it has a very nice compact representation. HW, we can see a matrix trace of in the middle. Middle is exponential transformation of W Hadam product. W, the circle is Hadam entry-wise product. So it looks like this has a nice compact mathematical representation. But on the other hand, computationally, this is very expensive because W itself is D by D matrix. And the exponential of this D by D matrix computationally is very, very expensive. So if we talk about the property of the Dagny's function, we know it is non-negative, non-convex, continuous, also differentiable, but on the other hand, it's computational expensive. So the 2018 NIPS paper provide this mathematical necessary sufficient condition for characterizing DAG, but it doesn't tell us what is the more efficient optimization procedure in order to solve the optimization problem. So using this nice result, we can reformulate our previous optimization problem by changing the DAG constraint by this equality constraint, right? So this becomes minimizing the loss function plus some penalty term subject to an equality constraint. Working with the equality constraint is much more convenient than the previous one. Yeah, previous one, we have to deal with this. This is some qualitative constraint. All right, so let's see. Can we use some classical optimization problem? So at the beginning, we start with leveraging the classical augmented Lagrangian algorithm, because this algorithm is particularly useful to deal with the equality constraint. So we can write down the augmented Lagrangian function in this equation 13. Yeah, this is the original objective function, loss function, penalty. Here, we only need to add two additional terms, alpha times the Degner's function. This is rho times squared Degner's function. Alpha is called Lagrange multiplier, and rho is called augmentation parameter. So definitely we can use this method. So this method itself is the dual ascent algorithm. So given for a predetermined alpha, we can compute the minimizer of W alpha in 14, and then plug in to the objective function. It becomes a function of alpha, and then minimize this function over alpha. So iteratively, we can get the solution. But on the other hand, if we really want to adopt the classical augmented Lagrangian method, we will actually encounter some problem. So I will show you where the problem comes from. So in this iterative approach, we can see we update W by solving this unconstrained optimization problem. And we also want to update the other two parameters, alpha and rho, according to the classical rule. So at this moment, we can see alpha will be updated additively with this is step size beta. But this one involves the Degner's function at the current weighted adjacency matrix estimate. So because of this, computationally, the procedure, the computational cost is extremely heavy. So that's why the limitation of using the classical augmented Lagrangian algorithm is slow convergence and very high computational cost. And the major reason is this classical method need to deal with the computation of this Degner's function. So this motivates us, the procedure. We want to design some optimization iterative procedure that can get rid of this term. If we can get rid of term, the computational cost will be lower. Right, so this is our proposed flexible augmented Lagrangian algorithm for solving the optimization problem. So instead of using the classical iterative approach, we want to, we allow the updates of alpha and the rho in a flexible manner. As long as they satisfy these two conditions, then that's fine. So as we can see, the computation of the Degner's function is no longer here. So that's why, intuitively speaking, the method will speed up the computation. All right, I'll show you some theoretical guarantee. So this is one of the theoretical insights. We want to study whether using our new procedure will achieve global convergence of the algorithm. So this result tells us, indeed, we are able to, the algorithm converges to the unique global minimizer. So I want to skip technical detail, but the major conclusion is, this method indeed guarantee global convergence. All right, next one. As a statistician, we really want to know the statistical property of the related structured learning method. The structured learning method is different from parameter estimation method. Here we are learning the structure, not only the structure, not only the parameter, but also the structure. Right. So in order to evaluate the performance of structured learning, we want to use some appropriate metric. So this is the metric used in our setup. This is the structural Hamming distance, SHD, between the learned weighted adjacency matrix W and the underlying ground truth W star, right? And this structural Hamming distance can be broken down into three terms. For the first term, EX. EX corresponds to the number of extra edges. In other words, people call it the false positive, for the number of false positive. And then in the middle, MI refers to the number of missing edges or the number of false negatives. And the last term, RV, RV corresponds to the number of reversed edges. So you can see the edge for the sign. This is positive, this is a negative, and this is negative, this is positive. So altogether, two cases give us the total number of reversed edges. And using this structural Hamming distance, we are able to define two types of consistency when the time length t diverges to infinity. The first one is the typical type of convergence for parameter learning, right? The parameter in our setup corresponds to the edge parameter. So as long as the Frobenius norm of the difference between the learned weighted adjacency matrix and the ground truth converge to zero, then the parameter estimation will achieve consistency. Moreover, if we want to assess whether the causal DAG structure reconstruction achieves consistency, we can use the second one. So the second one, with probability tending to 1, the structural Hamming distance between these two is equal to 0. So in the following, we want to study under which conditions the first consistency or the second consistency achieved. Ideally, we hope two types of consistency are achieved. So let's see, we have different scenario. So at this moment, we can see we have two types of a structure in mind. The first one, we want to deal with the DAG structure constraint. Secondly, we want to deal with some sparse feature because this is a high-dimensional inference problem. And usually, these two types of features, they are not identical. So in order to deal with two types of structures simultaneously in a unified fashion, we introduce an expanded estimator. So this time, in 26, we introduce another parameter, kappa. Kappa corresponds to some upper bound of the Dependencies function. Kappa can be 0 or 1. So if kappa equal to 0, the upper bound is 0. So that means the Degner's function must be 0 because Degner's function is non-negative. So this corresponds to we want to impose the Deg constraint in the estimation. And if kappa is equal to infinity, that means we don't have upper bound for the Degner's function. So this time, we will actually remove the Deg constraint. So the value of kappa from 0 to infinity can give us two different scenarios. Similarly, eta. Yeah, eta is usually the regularization parameter. So if eta equal to 0, then it will not use sparsity regularization. If eta is not equal to 0, then the sparsity regularization will be incorporated. So altogether, there are 4 different situations, right? So for example, the first one, if kappa equal to 0, eta is not 0, then this corresponds to the our proposed, the Deg constraint regularized estimator. And if we want to compare with the estimator without the Deg constraint, we can just set kappa equal to infinity. So altogether, using this expanded estimator, we can cover 4 different type of estimator. All right, so scenario A, without sparsity regularization. Scenario B, with sparsity regularization. The theoretical results are somewhat different. So let's see. So scenario A, we don't have regularization parameter, so eta equal to 0, right? So in this situation, the first case is I don't want to use the Deg constraint. And the second one is I do want to use the Deg constraint, and I want to see what will be the difference between the resulting theoretical results. So in this case, case one, no Deg constraint and no regularization. So in this situation, we can see the result is not good. Yeah, actually, we cannot achieve the Deg reconstruction consistency, although the edge parameter consistency can be achieved. So this part highlighted, this part tells us the edge parameter consistency can be preserved. However, the structural Hamming distance is always strictly greater than 0. So it cannot achieve the causal Deg structure reconstruction consistency. So this is the first result. This result can be useful to compare with the next one. Yeah, next one, we want to incorporate the Deg constraints, but still we don't have the sparsity regularization. So in this case, we can see that the results actually get better in the sense the structural Hamming distance can be always less than equal to some upper bound. And this upper bound will be equal to 0, small o1, when the true graph is dense. So in this situation, if we are working with the dense true graph, then the third result tells us the causal Deg structure recovery consistency can be achieved. So combining with the previous result 2 and the current result 3, we have some takeaway. So without using the sparsity regularization, then incorporating the Deg constraint is necessary for achieving Deg recovery consistency. All right, next result. The next scenario B. Scenario B, I do want to incorporate sparsity regularization because many times in high-dimensional inference, people want to use penalty at one penalty or weighted at one penalty. So in this situation, let's see, what can we learn from the this study? All right, so case 3. Yeah, case 3, I want to start with the method without using DAG constraint, but regularization is used. So in this situation, the result is pretty good. As we can see, the two types of consistency can be achieved simultaneously. Yeah, this is the edge parameter consistency. And the next one is the structure learning consistency. So both type of consistency are achieved. Then at this moment, probably we will, if both type of consistency are achieved, we don't need to consider other situation. Yeah, this is partly true. So let's see, the last case, case 4. Yeah, case 4, I want to incorporate both DAG constraint and regularization. So we will have this, the last result. Last result tell us, again, both type of consistency can be achieved. So at this moment, people will ask, what is the distinction between this result and the previous result? So in this situation, we are actually working with the scenario that sparsity regularization is imposed. So the conclusion is whenever the penalty or the regularization is used in appropriate way, then the DAG constraint estimator will achieve the same parameter estimation and structure recovery consistency in a way similar to using the estimator without the DAG constraint. However, the advantage of incorporating the DAG constraint is to improve empirical performance. So this is the advantage, of using the DAG constraint when the penalization or sparsity regularization is present. Right. I'm going to present some simulation results. Yes, thank you very much. So I'm going to omit some of the all right, simulation result. So in the synthetic data analysis, we want to look at different kinds of network graph with varying complexity of the underlying DAG structure. So the first one, second one, third one, and the fourth one. The first one is relatively simple. The last one is more complex. So I'll show you some numerical results. So we generate data. So comparison, different method. So this one, we want to compare the structural Hamming distance. So vertical line corresponds to some log transformation of the structural Hamming distance. The lower, the better. So our method corresponds to using the DAG constraint combined with weighted L1 regularization. So this method gives us the lowest value of the structural Hamming distance. So overall, this method has the best performance. Yeah, we can look at other examples, so I'm going to omit. So I also want to illustrate some comparison of the estimated network. So we did the simulation for 100 times, and then we randomly pick up one data set and the corresponding graph estimate to compare different methods. So in this figure, this is the true network, and the other 4 corresponds to the reconstructed network using 4 different methods. The top 2 without using the DAG constraint, and we can see the structural Hamming distance, the value of the structural Hamming distance are much larger. And at the end, we want to use the DAG constraint. This one uses standard L1 penalty, and this one using the weighted L1 penalty. So this figure tells us, if we look at this performance, this method has the best performance in achieving the lowest value of the structural Hamming distance. Right. And we can also compare the computational or numerical performance of our method and the classical augmented Lagrangian method, because we claim our method is computationally fast. So this gives us some graphical illustration. Yeah, on the left-hand side, we want to look at the error, the change of the Frobenian norm between the estimator and the ground truth. So our method, we can see, yeah, our method will converge within about 5 steps. Yeah, our method will converge within about less than 5 steps. But the classical augmented Lagrangian method will converge more than 10 steps, right? So we can see from this one. And the right panel corresponds to the comparison of the CPU time. So this is our method using this box plot of the average CPU time across 100 simulation runs. So our method indeed has runs faster than the classical method. All right, real data analysis. Yeah, for the real data analysis, we have 2 different data. The first one comes from neuroscience, where we want to analyze the neuron spectrum data. So this data comes from a paper published in Nature Neuroscience. The data set contains 89 recording sessions, each session corresponding to an experimental period, and the total number of total duration of approximately 24 hours. And we do some pre-processing. The data contains altogether about 600,000 stems from more than 100 neurons. Yeah, in this situation, if we have 100 neurons, then the total number of parameter will be 10,000, right? So this is a high-dimensional parameter estimation situation. All right, so we can compare the reconstructed network. The left one did not use the DAG, did not use the DAG constraint, and the right one used the DAG constraint. So for this data set, it looks like the difference is not that much, because for real data application, we don't know whether the underlying structure is DAG or non-DAG, right? So we want to apply our method to this data set to see whether the difference is substantial or not substantial. So for this data set, it looks like the 2 approaches give us some results comparable to each other. Now we can also look at a different data set. Oh, by the way, this is some subgraph. Using this subgraph, we can quickly find out some of the cycles or loops in the left plot disappear from the red one. The red one, because we use the DAG constraint. So DAG constraint will eliminate those unnecessary, especially weak, the weak edges. The second data set comes from internet protocol television viewing record. The data set is about TV channel watching events from over 10,000 viewers in Guangzhou in the entire August of 2014. So after pre-processing, we obtained the data with a total of more than 800 timestamp extracted from 81 channels. Total time length is 32 days. Yeah, 32 days. And the goal is we want to explore the causal effects of viewing behavior among different channels. Yeah, some people prefer to look at channel related to sports. Yeah, some people like to view channels related to entertainment, etc. So there are many, many channels. They compete with each other, and how those channels will interact with each other and affecting the viewer behavior. Right, so this is the network graph learned from the data. The left-hand side didn't use the DAG constraint, so you can see it gives us a very dense structure, and the right-hand side used the DAG structure, so it gives us a little bit sparser structure. We can also quantify the difference between the two different methods. One without using DAG structure constraint, the other one using the DAG structure based on calculating the predictive log likelihood for each of the methods. So again, this computation indeed tell us incorporating the DAG constraint will increase the predictive accuracy. All right, I think I'm at the end of the talk, so it's a quick wrap up. All right, so as a summary, in this work, we develop a flexible, augmented Lagrangian optimization method that will give us provable global convergence and achieve computational efficiency gain over the classical augmented Lagrangian algorithm for learning the causal DAG structure from multivariate temporal point process data. Analytically, we quantify two different types of effects. One is acyclicity constraint for DAG structure, and the other one is the sparsity regularization for sparse feature. Yeah, usually they play different role. So altogether, we have 4 different cases summarized in this table. And the last one is the approach we recommend. So using both DAG structure constraint and the sparsity regularization. Yet also there are some future study that needs to be developed. For example, how can we quantitatively compare the effects of the DAG constraint and sparsity regularization in more general situations. And also because the conditional intensity function itself is highly nonlinear, so it will be more interesting to utilize deep learning method, artificial neural network, for the analysis of the underlying random process. So thank you very much for attention.
Okay, so we have time for some questions. Go here first.
Thank you, Professor Zhang. It's very interesting work. And My question is, if I want to use your model into maybe financial risk network modeling or any other things, is there any limit about the network size? I can see you have maybe 80 or 100 more nodes in your network. Is it possible to use maybe thousands or more?
Yeah, that's a good question. So that's why we mentioned in the here, we really need to want to have more refined algorithms in order to analyze more challenging situation with large-scale data sets. Yeah, so far the number of neurons in our study is about 100, because 100 square is already 10,000, right? So back to your question, if you have thousands of nodes, yeah, which is typical in many other applications like citation network. Yeah, I talked with other people using citation network. They actually developed some neural network approach which can efficiently handle the computational aspect. But so far I have not yet try those kind of data, because for this one, the computation is already a big challenge. Yeah, that's a very good point. Yeah.
Thanks for the good talk. And I have some question about the uncertainty quantification of the result. So I mean, when we are using the scoring rules, we have three parts, right? The first part is like whether we missed something, whether we add something more, and whether we have make some contradictory edges, right?
Worst.
Yeah. So when we are doing these things, have we considered anything about uncertainty quantification of these or statistically significance of these edges? Because if we only use the point estimate, sometimes if it's not significant, that does not actually make too much difference if we say it's significant or not, right? So if it's positive or negative, if it's not significant, I mean, sometimes it will change some scoring rules, right? So have you considered anything about the uncertainty quantification of the ages, or how much is it?
Yeah, thank you for the great point. If you ask me whether I considered or not, yes, I did consider those points, but those issues are so challenging for me, I'm not yet able to deal with at this moment, because you have to consider several issues. First of all, you have to deal with the computational issue. If you're not able to solve the computational problem, you are not able to move forward. So we spend a lot of time in devising some efficient computational algorithm in order to numerically give us some solution. And this solution has provable convergence property so that we can trust that result. And then using that numerical solution, we want to explore some statistical property. Yeah, so far, as you mentioned, we only discussed a limited number of theoretical insights. The next one, I think the next important or critical statistical issue is talk about inference procedure, like uncertainty quantification. Yeah, that one, is still beyond our limit at this point. I remember some other audience asked us whether we can develop some statistical test statistic in order to check whether the underlying graph is stacked or not. Yeah, even for that problem, we haven't able to come up with a good statistical statistics as a test statistic. We are still thinking about it. Yeah, but I'll keep that in mind. Yeah, thank you.
So thank you very much for your presentation. I have a question regarding, for example, consider we have a couple of time series which are forming the equilibrium in a market, economic equilibrium in a market. Can we use this model to ascertain the dynamics and the direction of causalities among those time series? And for example, I assume that those time series play the role of each nodes in your model.
Yeah, very good question. Let's see. Yeah, I would say, yeah, this approach is designed for certain type of data. It's actually not applicable time series data. For time series data, the time points are equally spaced. For equally spaced time points, we cannot define, yeah, actually we cannot define the Yeah, we cannot define the conditional intensity function. This conditional intensity function is defined for event time points, which are random and are not equally spaced. We can check. For equally spaced time points, this conditional intensity function doesn't exist. So I thought about this question for a while. Why people didn't use this for time series? Later on, I found, just because the current setup used the conditional intensity function, but the intensity function is not applicable to time series data. Yeah. So hopefully this will answer your question.
Yes, just since I'm working with time series, the question is there any method that we can use to ascertain the dynamics of causality among time series data?
That's a good question. Yeah, I think there should be. Yeah, I should be, but not in my mind at this time. Yeah, I can double check later on.
Okay, I'll be in contact. Thank you.
Hello, all right. First of all, thank you very much for the presentation. It was extremely insightful and really interesting. And I would like to ask you about the lag between the action and the reaction, let's call it that way, because on the example that you provide on the neurons, I imagine that the trigger neuron triggers some signal and then the inhibitor reacts almost immediately. What if there will be a lag between the action and the reaction? Does your model still works? And if yes, what is the sensitivity on that?
Yeah, you are asking some question related to the time lag?
Yeah. Please come again.
I'm not quite sure whether I fully understand your question. Are you talking about some time lag or?
Yes.
The time lag, yeah, for simplicity, we just use short-term historical event for computational simplicity. So that's why the time lag size is 1 unit time. Later on, we try to do some kind of extension that can extend one time lag to multiple time lag. But from one time lag to multiple time lag, the corresponding theoretical study needs to be re-examined. Yeah.
So the lag is predefined from the model and then you run the model. In the sense that you've used the -1 here, I believe it's, it's in the morning, I forgot this Greek letter.
T minus 5. T minus 5 side. Yeah, the time lag, the window width.
Yes, it's predefined before you run the model. It's not that the model can capture whether it's sometimes 1, sometimes 3, and still.
Yeah, that's possible. Yeah, that's possible. Methodologically, I don't think there is constraint on the choices of the site to be constant or varying, right? But theoretically, this will make a big difference. Yeah, sometimes we really need to make sure the theoretical results can be justified, and then we use the related methodology. Yeah, from methodological point of view, no constraint on the choice of site.
All right, thank you.
Theoretically, we have to figure out result that can be justified. Yeah, thank you.
Okay, so I think we might leave it there. If there are further questions, I'm sure Professor Zhang will hang around. But let's thank Professor Zhang just one last time.